Hello, welcome back to the fourth of the four probability videos for Geography 300, Geographical Data Analysis. This video is taking the ideas from probabilities and distributions. In fact, you can see I've left the continuous normal distribution here, and moving towards what I have here as z-scores, our first approach at basically coming to an inference. So to put this into a very simple analytical process, we may wish to know if there's something unusual about the age distribution of different counties. So I can then say, as the general problem, age distribution of West Virginia counties, Mon County in particular. I collect the data. And so I go to the census, I find the median age of every county in the state. And I might plot that out, and it might look a bit like a normal distribution through my descriptive statistics. I get the mean, I get the standard deviation, and I have the value for Mon County. These are not necessarily the exact numbers, they're general idea, but don't take these as the true values. Mean of 44.3, standard deviation 7.2 years. Mon County's median age, 29.7. So you might say, is there something strange going on? Okay, maybe there is something unusual affecting Mon County compared to the rest of the state. So I can set up my inferential test. So I can then use this kind of normal distribution to evaluate this. If Mon County's value fits in, if it fits in, it's going to be closer to the middle. If it doesn't fit in, it's going to be further out to the edge. But I have a mean of 0, I have a standard deviation of 1. Trying to do this kind of calculation on the original mean and standard deviation would be very difficult. The math would be much harder. I'm not showing you the math as is because it's kind of messy and complex. The math would be much worse, except for having a mean of 0, a standard deviation of 1. But we can use what are called z-scores to make that transformation. So I can get a z-score by taking the original value, subtract the mean, divide by the standard deviation. This is then going to be minus or negative 15. Negative 14.6. To make life easier, I'll turn this into 7.3. Divide by that standard deviation, and I get a z-score of -2. Now I can assess this question by looking up the probability. Instead of x, this could become z less than 2.0. And that's going to be this green area, a little bit more than the -2.4 I had before. A z-score of -2, a probability of something strictly being less than that will be again, I don't have the numbers exactly memorized off the top of my head, so I'll put approximately about 0.025. If you recall, I had said earlier when introducing the normal distribution that about 2/3 was within 1 standard deviation, about 95 within 2%, about 99% within 3 standard deviations for a normal distribution. Though that area outside, that not within 2 standard deviations, is split between above and below. So the probability of z less than 2.0 should be about 0.025. This is a very frequently used term and concept called the p-value. It is basically the probability that our data supports this null hypothesis. The value of Mon County matches the rest of the state. What we're saying here is there's only a 2.5% chance Mon County fits in with the rest of the state. That would seem to be pretty low. There are no strict, cut and dry thresholds. It is very common to use either 5% or 10%. But there's nothing magical about those numbers. What then ends up happening, we might say, I'm going to use this for some further action, some further investigation. Maybe I am trying to run a promotion activity aimed at the younger populations within the state. Mon County is an unusual match and is below the mean, so I might then use that low probability that it matches to say this would be a good place for that program targeting younger people in the state. So we use that to guide some decision, to guide some action. Where you set your threshold, here 0.025, is that below whatever decision-making threshold I would have? Ultimately, that depends on the cost of being wrong. In the example I just gave, running a program to, say, promote activities that keep young people within the state of West Virginia. The odds of if I get that wrong, okay, I might have wasted some state money because I picked the wrong county. There weren't many young people getting the message. Yes, that is a cost. I want to make sure I'm doing well and using state resources wisely. But the cost of being wrong may not be that great. On the opposite, the most stringent I have ever seen is where people did not release any p-value, did not release their scientific results until the p-value was less than 0.00001. Extremely low. That means there was basically a 1 in 100,000 chance they were wrong when they made their announcement. When you are doing the announcement of, we have discovered the Higgs boson, a new particle in particle physics. Everyone had suggested, yes, this thing exists, but it had never been detected until about 10 years ago. This is a really big deal, was a really big deal in physics. It would be on the top headline of every science section, every newspaper worldwide. If you get that wrong, now the wrong information is in the top headline of every newspaper science section worldwide. That's a really big price for being wrong, if only for the reputation of those scientists, of those physicists, of their lab, and everything else there. You want to be really, really, really certain when you do that. So the cost of being wrong can guide that threshold for making your decision. But in every single case, we are setting this up, and I'll reinforce this later. Essentially, the not very interesting setup is here, the null hypothesis, what's called the null hypothesis. The value of Monk County matches the state. And the data is suggesting it's a low probability of that. It doesn't match. That is how well the data matches that hypothesis. It is a slightly different thing than the hypothesis is true, because the data could be wrong. In this case, to then relate to a process that can explain this, the university, the presence of WVU, and all the students associated with it would drive down the median age. And so there's a process that explains why Mon County doesn't match the rest of the state. And because I have that other process from outside information, I am willing to then believe that this hypothesis, that the value matches the rest of the state, is indeed false. And I have a reason to trust my data. So here we have this process of using probabilities and distributions to conduct a simple inferential test and reach a conclusion: Mon County's age structure is different from the rest of the state. If you have any questions, please feel free to ask in class, send me emails, whatever you need to do. Have a good one. I'll see you at the next video.